Okay, if you are on pace with where you should be in this class today on September 23rd, where you should be, what the thing that is due is workbook 9.3. Workbooks 6 through 9 in Unit 2 cover the standards G.co.3 and G.co.5, and you will have little tests that are like one little test that covers G.co.3 and one little test that covers G.co.5. By the time you're done with the unit, which it goes through workbook 11, by the time you're done with the unit, you will also cover G.co.8. So today in our live lesson, we're doing G.co.3 and G.co.3 and G.co.5. And what I'll do is I'm going to reteach things and then do examples like the problems in the evaluation, not the actual evaluation or assessment or test or whatever you want to call it. So, okay, so GCO3 says, given a rectangle, parallelogram, trapezoid, or regular polygon, describe the rotations and reflections that carry it onto itself. I want to kind of break down that thing just so that you know what to expect. I think you guys know what a rectangle, parallelogram, trapezoid, or regular trapezoid is, but do you guys know what a regular polygon is? You know what regular polygon means? What does that mean? Nobody knows what this is good. See, this is why we're going over this. How about rectangle, parallelogram, and trapezoid? You guys are good with those? I assumed that you were. Am I right? Okay, good. Yeah, I like that. Okay, a regular polygon is polygon means like more than 3 sides, like a shape with more than 3 sides. But regular means it has equal sides and equal measures. So like a square. A square is a regular polygon. Or an equilateral triangle is. Equilateral triangle. Or even if you said a stop sign, like a stop sign has, I can draw it nice-ish. All of these sides are supposed to be equal, like they're all equal. And so that's a regular, you could say that was a regular octagon. Regular just means all the sides are equal and all the angles are equal. Or congruent is the fancy word. Describe the rotations, so that means turning it, right? And reflections that carry it onto itself. So rotations, I kind of did this little symbol on the outside, like this little spirally thing, so that you're rotating it. And when they describe those, they talk about it, rotate it about point blah, blah, blah. Or maybe they'll say rotate it about the origin, because technically the origin on a graph is a point, right? So let me just show you an example of this using this cool technology I have here. You guys ready for this? If I took this and I'm going to make a copy of it and then I'm going to paste it and then put it right onto so technically, and then it says carry it onto itself. So here I have this rectangle that I'm floating around. If I were to carry it onto itself, that means literally I'd put it right back where it came from. So that's carrying it onto itself. So if I took that, see, I just moved my hand a little bit. Pretend like it was on itself. Well, okay, close enough. If I were to rotate it like this has still rotational, so that is the only time that it's mapping it or carrying it onto itself is when it goes back to the exact same position in the exact same order. But this is rotating it. So where would you say that point of rotation is? Ish on what I'm rotating right now. To me, it looks like it's in the center of the rectangle. Would you guys? Isn't that weird? Okay, so I'm going to map it back onto itself. So that's what that's what mapping it onto itself means. Is it goes right back where you got it from, and that carry it onto itself. So with this, with these rectangles, I could rotate it about the center, about some point that's in the center there. And I'd have to go all the way 360 degrees. Would map. In other words, carry. rectangle ABCD onto itself. Oh, it's self. It's, I should have put extra stuff in there. Let me try this again. It's self. Okay. And then if I had another regular polygon, so let me do, if I had an equilateral triangle, for the sake of what we're talking about, pretend like this is an equilateral triangle, and that will be HIJ. How many degrees, if I rotated it about the center, and let me do that trippy thing again that hurts somebody's eyes. Amaya, that was hurting your eyes, right? Sorry. Okay, if I rotated that, oh wait, I have to copy it first. Dun, 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 copy and paste, and I have to line it up. Basically, the belly button, it's like weird, huh? Okay, now if I rotate that, how many degrees do I have to rotate it before it looks like the exact same shape? See, and my drawing was not super great. But if I rotated it this many degrees so that lined up like that, like I could scoot it over like it's supposed to be. Well, scoot it over. Come on, scoot it over there like it's supposed to be, then it's lining up with itself. It's mapping it onto itself. Especially if it'll hold still, but it won't. Then that's mapping it onto itself. Or I could keep on going. And so that it goes over there like that. It's still mapping it onto itself. So technically for an equilateral triangle, you would have to rotate it. There are 3 different places where it's the same thing. So like all the way around, right? That's 360. Then a third of it and a third of it. So it's basically like doing 360. Ooh, I'm going to delete that because it's going to be weird. I agree. Delete. Okay. So for the triangle, 360. Oh, I need a pen. 360 divided by 3, which is 120 degrees, maps the equilateral triangle onto itself. Is that how you spell itself? See, I just am confused. Is anybody good at spelling those things? See, that's why I'm stupid. Okay, not stupid. I'm less strong. Okay, so this is the idea. Is it's mapping it onto itself. We could keep on drawing figures, and basically what you're doing is if it is for any regular polygon, let me make this fancy rule because this is the rule. For any regular polygon, the rotational symmetry, that means it's going back onto itself, is 360 degrees divided by n, where n, oh, you can't see it, is n, where n is the number of sides of the polygon. So we did triangle because I had 3. And yeah, so if we had like an octagon, we would have to divide it by 8, right? Okay, cool. So that's the idea with that G code, with the rotations. So I'm going to split this up. And you can do that same type of thing, like with technically with, oh, in fact, let me just show you this one while we're on that idea and like the weird things that mess with your eyes. If I were to, let me undo that line first because it's going to mess with what I want to show you. Okay, delete. Okay, if I took this parallelogram and let me copy it, and now I rotate it, paste it, line it up, ish, whatever, it's close. Okay, pretend like I lined it up, and then rotate it. It would be the same shape if I rotated it. Instead of 360, I could rotate it 180. So let me delete that because it's really confusing, but then write this in here. So Parallelograms have 180 degree rotational symmetry. Because basically when you rotated, the E went to where G was and G went to where E was. Symmetry. Let me try to put the R in there. Symmetry. There we go. Yeah, spelling. Okay. Good. So that's rotational stuff. Now let's talk about reflections. I'm going to make that line again because that's what's next. So reflections, and I kind of gave a hint for reflections. Do you see the R and how I like put the reflected R on the other side of this thing? Reflections, on the other hand, have lines of symmetry, where if you had a line that you could draw and it would reflect it back onto itself. This one I cannot do with the cool, clever tools that I have. It does kind of look like scissors, doesn't it, Dylan? These I can't do these with the cool tools that are on here. The tools are not quite as cool as I wish they were. Okay. So lines of symmetry. Let me come back to, can I just click on it and grab this triangle, rectangle here? Nope. I'm going to borrow this. I'm going to have to draw another one. And then I'm going to come over here and paste it over here. Okay. Oh, we lost the bottom part of that letter right there. Okay. This one, we're going to do this in, what color do I want? I'm going to do it in light purple. Okay. What happens with the lines of symmetry is basically you can think of it as folding it in half, where all of the corners are still going to match up with another corner. So like with this triangle, with this rectangle, if I folded it across this line, then basically A would fold over and line up with B, and D would fold over and line up with C. And then that means that is a line of symmetry. This is a line of symmetry. And to be complete about what happens with the line of symmetry is basically, you can also think of it, and I don't know, there's not really a nice way to do this, to like explain it on here. But if you were imagine that this is a pole. The line of symmetry is a pole, and that's just like a poster that's sitting on the pole. And you only had it attached like to the pole up here, like on this part of the pole. It could technically keep on spinning around the pole, right? Just keep on spinning and spinning and spinning. That would be a reflectional symmetry, because it would look back like it could spin around and then it would look like the exact same thing. So it'd keep on spinning around. So, reflectional symmetry. So those are the lines of symmetry. I could also have, so ready for your mind to be a little bit blown. I could also have a line of symmetry right here. And then same thing, I could fold it across that line, and then B would go where C was. I'm not going to draw those other lines because I think it gets confusing. I'm going to take them off, in fact. B would go where C was, and C would go where B is. Like they'd switch places because you could fold it there and it'd line up exactly true. But now look at this, the parallelogram. Is there a way that I can fold this parallelogram where it would, I can't grab it all like that. Hold on. No, I can't do that. Okay, is there a way that I could have a parallelogram and have lines of symmetry with a parallelogram? Is there a way that I can fold this parallelogram where all the corners are going to line up? And this is kind of what makes the big difference between people who can see geometry in their head and people who can't see the geometry in their head, and it's kind of different. If I had this parallelogram, some people just do the classes out of order. So if they're in 11th grade, it's not a big deal. And I think there's even some students that are in 9th grade. So it's all good. So let's just say this one is, where do we leave off, Jake? So this is K, L, M, N. Can you guys think of any lines that you could draw on that, anywhere that you could fold that parallelogram where it would map it onto itself, where it would like fold it exactly right and line up with itself? KM. Okay, so let's say that I did that. Let me see if I can, what's the best way that I could try to do that? This one doesn't have reflecting. Okay, so the suggestion is KM. So let's look here. If I took a line across KM, I can see, and then I'd have to be, it'd fold perpendicularly. N would actually end up right there, and it's not going to line up. See what I'm saying? It looks like it should, but if we actually folded it across that thing, it would not line up. So KM would not line up. Line up with L. I should put would not line up L and N. L and N. So it's not a line of symmetry. As long as it's a parallelogram and not a kite, because if it's a kite, do you guys know what a kite is? Or a rhombus, which a rhombus is a type of regular polygon. In other words, if all the sides of that, like K, L, and L, M, and L, like if all these sides were the same, like if this side was the same length as this side, which is the same length as that side, and the same length as that side, if it was one of those, then it would be, but this is not an example of that. So, okay, so that's lines of symmetry, and they'll ask like what maps it onto itself. So they will have mapping onto itself is the phrases that they use. So you're looking for the phrase map onto itself. So will a quadrilateral map onto itself using a... Okay, so let me just draw another thing. Let me just give another example. Okay. And I'm going to do, so what I'm going to do now is I'm going to give examples from the test. So this is me generally teaching you and giving a couple little examples, but now I'm going to give you examples from the tests. So, yeah, from the test. So here's a question similar, but not exactly to one on the test. I'm going to put lined paper here. Makes my life a little bit nicer. Oh, I want that one. Okay. So let's just say we had this shape. I'm going to draw it, and you guys are going to tell me what that shape is. What's the name of this shape? What is the name of this shape that I'm drawing right now? What is the name of this shape? Isn't it lovely? Thank you. What do you call that shape? Especially if my lines were straight. But pretend like they are, okay? Be nice. Actually, what happened is I cracked my screen, so when I'm writing here, this part of my screen, I should just write somewhere else, but this part of my screen makes everything go like all wobbly. What is the name of that shape? It's a pretty one. This is where you guys said you knew what they were called. I'll give you a hint. It's in this fancy pantsy definition that was typed up. Oh, trapezoid. Thank you. Good job. This is indeed a trapezoid. Okay. So looking at that trapezoid, is there any sort of rotational symmetry? Besides, put besides, which rotational symmetry means that there's something besides 360 degrees. Is there a way that I could rotate that figure? So, is there a way that I could rotate that figure less than 360 degrees that would make it look exactly like itself? In other words, can I take my weird thing and rotate this? Oops. Wait a minute. Hold on. Ta-da, copy. Da-da-da, paste. Line it up. Okay. Is there a way I can rotate this where it would be exactly the same thing? Anything less than 360 degrees. You know what? Honestly, Brendan, when I was in college, like I'm going into math, right? Looks like a trap. I like that, Dylan. So when I was in college, we had a task on a computer. They're like, here, get on the computer, because one of the things that you can do with the constructions is use a program called GeoGebra. So they're like, get on GeoGebra and create a rhombus. And I'm like, what is a rhombus? I had no idea. I had no idea what a rhombus was. And I had finished all of my high school and everything like that. Had no clue. And then I saw it, I'm like, oh, well, I feel dumb now. Rhombus, by the way, is a four-sided object that has four sides that are exactly the same length. And you can see that clearly. This side right here, this side is way shorter than all the other sides, so that's clearly not a rhombus. If you fall on top of a trapezoid, then you die on the inside. Okay, so it looks like a trap. So it is a trapezoid. And is there any rotational symmetry? If you go all the way around, besides 360, can you get it? Rotational symmetry? No, because we cannot rotate it anything less than 360 and get it. Why is this thing up? Go away. I don't want you there. Can you go away? Why are you up? Okay, doesn't matter. Why is it up? Okay. Does it have reflectional symmetry? Is there a line of symmetry? So the next question is line of symmetry. That maps it onto itself. Is there a line that I could fold it across where all the points would line up? In fact, let's give it some letters. We can give it we'll give it letters like this, because I can see that Evan is in class and he has 4 letters. I could do Nick too. I can't do Maya. Why can't I do Maya? If we have trapezoid Evan, does trapezoid Evan have a line of symmetry? Actually, the line doesn't actually have to be part of the figure. It doesn't have to be part of the graph. It could be something totally new and separate. In fact, Dylan, what you said is middle flip is probably the best. I think that's what you're trying to talk about. Like, so if I were to take a line and draw it right here through the middle, can you see if I flipped it on that point, like that line, folded it there, flipped it, that would be the same thing. So that center line, so that would be yes. It would be that line-ish, right? And so that would be a line. It would have one line symmetry. Maps it onto itself. It has, yep, there we go. So Evan works, but Maya, as in Maya Rogers, would not work because there's 2 A's. It just wouldn't work for this. But that could be a triangle, right? All right. So then, okay. So then next one. How do I get rid of those pages? Because I don't want them there. And I don't remember how to get rid of them. This thing? Yay. Okay, that's all I have to do. All right, let's do this. If I had this figure right here, and pretend again like I draw really nice, but you can use the graph to see that what it should be, right? If I had this one right here, and let's do Nick. Okay, this First of all, do you guys know what this is called? Do you know what the name of this polygon is called? Square. Fantastic. What's the other word for it? We just talked about it. It is technically a rectangle. It is a regular polygon. It's the one that starts with the other one that starts with an R that I talked about me not knowing. Rhombus, fantastic, Dylan. In fact, let me just show you some notation that they use to show that two sides are the same. They put like one tick mark in the middle of them. Look, if there's only one tick mark, that means that those are the same. In fact, on trapezoid Evan, I could say that this side and this side are congruent. Those are the only two that are congruent. So if they have the same lengths, they have like one mark with them. So that's true of all these. This shape is indeed, it's a rectangular, it's a regular polygon, it's a square, it's a rhombus. Technically, it could be, it can't be a kite. So it fits all of those. The best description that we would give is a square, but all of those work. Okay, now what is, so here's the question, is which transformations, so that's rotating it or reflecting it, which transformations could map square nick, that looks funny to say square nick, onto itself. That's how you spell it itself. That I can see it. So which transformations could transform square nick onto itself? What could we do? Purple is the color I'm writing with, which has a question that you're supposed to write. So any transformations, what is one transformation that you could see that would map it onto itself? So you could rotate it. In fact, how many? So let's just talk about the rotations. If we were to talk about the rotational symmetry, how many degrees could you rotate it? Rotate it. How many degrees? How many degrees would you say? Do you guys remember it all the way around is 360, right? It's regular. Yes, fantastic. Oh man, Dylan, you got it. So we could do 90 degrees. We could do, because let me show you. Let me do the trippy eye thing. Right. Copy, paste, put it onto there. All right. Now, so this is 90 degrees. Pretend like it was perfect, but it's not. There's 180. There's 270. And there's 360. So again, let's go over the thing that we talked about earlier. We said that we would have to take 360 and divide it by the 4 because there are 4 sides to this regular polygon, which is 90. And then it's all the multiples of 90 that get up to there. So 90, then 180, get up to 360, then 270, and yeah, and then I'll put here 360. So notice that the 9 and 18, that's in 180, and 27, those are all multiples of 9. Okay. How about reflectional symmetry? And so we're going to talk about how many lines of symmetry. How many lines of symmetry does this one have? And it's a square, so it's going to be a little bit different than just a regular rectangle. How many lines of symmetry can you see? 4. So let's see. Dylan, describe what's one of the lines of symmetry that you see. NK. So that actually can't be a line of symmetry because you can't fold it across NK and get it to look like itself. But so NG would be very good, Maya. So like if you folded it across this way, Because it's a regular polygon, K and I would match up with each other. And then for that same, so we have, I'm going to put NC would, KI would. And then we don't have letters for these. I'm just going to draw them in. I'm going to change the color. So those are the diagonal ones because it's regular, then it would work. And then these right here. So there are indeed 4. Then the lines in the middle. Vertically and horizontally. Okay. Does that make sense? So that was like the brownish, whatever color that is that I drew. Okay, good. And then, yeah. Perfect. Getting this. All right, next one. Let me see. That's that one. Okay, this is another thing that they talk about with rotational symmetry. Let me come back up to rotational symmetry. We talked about it. This point right here, I'm just going to give a definition. This is called the center. And when we spun it around, that was the center of rotation. In other words, they say or of symmetry. I never called it the center of symmetry, but they did, and so we better know it. So that's a thing that you have to know. That's a thing. Cool. I think we've already covered that part. We covered that part. Okay, last thing is, okay, here's another weird one. This is going to be a weird one. Let me see. How can I do it? This is still GCO 3, but GCO 5 is really very related. So GCO 3, last question is, if I had, let's see, how can I draw this? Okay. Dun, 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 dun. Yep. So let's say that I started with this right here. I had this figure, and I'm going to give it some letters. Let's call it, what's the next one that we can do? We need 4 letters. Okay, I'm going to do my first name, B-R-I-T. And then, is that what I want? What's the best way to show this? That one's really a nice example that they have. Okay, so hold on. I think we need to review this. It does. It looks like a cartoon foot. Definitely. A boomerang is a good one. I'm from Australia, so I have to draw a boomerang. All right. I don't like this example. I'm going to do it anyway. Okay. What's the best way to do it? I think I'm going to have to change I. I'm going to change I because that'll be the best way to do it. Then it looks even more like a cartoon foot, but it's a weird cartoon foot. But okay, so there's I. I have this one, and then I do something to it, and you're going to have to tell me what do I do to this to make it look this. What could I do to quadrilateral Brit to get to quadrilateral brute? Okay. which is what I end up accidentally typing so many times because the I and the U are next to each other, and if I'm not looking, then I end up being brute. Okay, what could I do? And then it's going to be, let me give another letter in here. I'll put another letter right here, and it'll help us talk about it. Q. What could I do to quadrilateral Brit to get quadrilateral brute? What transformation can be used to show? So let me put the fancy question down. So what transformation could be used to show that quadrilateral Brit is congruent to quadrilateral brute? Congruent, do you guys know what congruent means? Okay, I would, yeah, reflection, maybe rotation is needed. If you're going to rotate it or reflect it, well, let's just start with reflection because that started first. What would you reflect it across? Yes, nice job. High five. High five. Yes, the 2 is in my 1's place value. Always starting. And I deliberately put letters, an extra letter in there to help it across. Reflection across BT. Okay, so we reflected across BT. And then, okay, wait, let me just go through these steps that you're describing, Dylan. Let's see if it'll work. Okay, I'm going to get this color. So if we reflect it, how many is this? 1, 2, 3, 4, 5, 6. If we reflect it across BT, so we go down 1, 2, 3, 4, 5, 6. Then it would look like this. So that's the reflection across BT. And then you said 90 degrees counterclockwise. So that means all of these would go up. Yeah, that could work. So that does work. And so this would be R. Once you do a transformation to it, they call it prime. Then this would be I prime. The little dot dash thing is called prime. Scoot it. And then rotating it, then you would like rotate everything so it would go 90 degrees. So one way is, yes, you could reflect cross BT, then rotate 9 degrees counterclockwise. Okay, there is one simple step that you can do also. So I'm going to go back to because Brendan, you answered, Dylan and Brendan, you both talked about reflection. So what could you just simply reflect it about? There's one reflection that will do the whole trick. Can you see it? Chelsea's getting it. Amaya's getting it. So you could, like, what they described was the rotation. We're just talking about the reflection. Let me just jump in, okay, just for the sake of time. If I reflected it across this line right here, across BQ, it would be the exact same thing. Does that make sense? Reflect across BT, then rotate it counterclockwise, or one thing would just simply be to reflect across BQ. Do you guys see that? So I'll put here either one work. Either of those works. One is more efficient, but they both work. It's not like the other one would be a wrong answer. Okay, so that is G.CO.3. And then let's go into the G.CO.5 questions. It's a longer lesson than I mean for it to be, but here we are. So, Okay, next one. Okay, let me do some other things, and it's kind of doing the same type of things as some other drawings. It's kind of going to be the same thing. Let me go like this. We're going to put it on a graph. So if I had a graph like this, and yep, and then I'm going to give letters to it. So let me do like this. So I need 3 letters. Who can I use? Oh, wait, we're going to use Maya now, right? So we'll do M-I-M-A-I-A, depending on how you go around it. You have to go back through it. But anyway, we had Maya, and then all of a sudden we did something to it, and now we have, so this is, so I mean to say this is G.co.5, because it's basically the same thing that you learned on both of them. It's just a little bit different stuff with it. Went from that to M prime, A and I prime, A prime and I prime. So we went from M-I-A to, or M-A-I, whatever you want to say it. It could also be my, not just Mia, right? Is really to get her name, we'd have to go around like this. We'd have to do M-A-I-A, but we just needed the 3 letters because you can't use A twice on one figure. Okay. How would they get, like, what is the way to describe how you would get from the one without the primes? And so this is also another thing you need to know. This is called the pre-image. Is before you do anything put. This is the before. And then this is called the image, which is also like saying it's the after. So what transformation would get us from the pre-image to the image here? So I'll give you a hint. It's either going to be a rotation or a reflection. So you said double reflection. Okay. So Dylan says double reflection. So what do you mean? And I'm going to tell you that this is a way of doing it, but it's not the most efficient way. It's not the shortest answer. But it works. Double reflection. And then that would be across what? Over the x, across the x-axis, then y-axis. Okay. And then, all right, we got the double reflection then. Okay, so this one is going to use a point that's not part of the actual triangle. The point, the other, I'll tell you, it's a rotation, and it's not part of the triangle. Yes, Dylan, you can rotate it 180. About the origin, look at you guys. Teamwork makes the dream work right there. So here's our origin, and if we rotated it, so let me just show you from M to M. If I rotated it from M to M, that's 180 degrees. So good, that's the best one, is rotate 180 degrees about the origin. But both are correct. So the double reflection is not false, but the rotation about the origin is the most efficient. So, okay, and then let me see. Okay, one thing that we haven't talked about that GECO 5 also includes is a translation. Do you guys know what a translation is? In geometry, I should say. What's another word for a translation? A movement. Technically, all these things are moving different triangles. Yeah. How about slide? slide, slippery slide. Yep. A translation is a slide. So you're like taking it and just sliding it over. And then even, yeah, you're just sliding it. So it keeps like, if we took Maya, the triangle Maya, and we just slid it straight down, so it was like right here, that would be, we're going to give it a different name. We're going to call this M prime prime. That's how you say it's a different one. M prime prime and I prime prime and A prime prime. That would be a, from here to here is a translation. How many units down did we go? 4 units down. Does that make sense what I just did? Okay, now they make it all weird. Okay, they're going to make translations really weird. They're going to go like this. So this is how they actually talked about that thing. So that translation 4 units down, the translation would be, actually, let me just make sure because I know how a lot of other people do it. Yeah, so they'll have the points on the graph. So they'll say, this is what they will say, because maybe they won't even graph it. They'll say that M right now on the original one is at the point, oh, dang it. Okay, is at the point 2, 3, and it's going to the point 2, -1. Because again, it moved it down, and up and down, remember, is only has to do with the yep, slide to the left, slide to the right. Okay, the up and down only has to do with the y, like the y point, the second point. So we have M, and then A was at the point 3, 0, and now A prime was at 3, -4, and then I was at 4, 3, and now I prime, I should put prime prime, I forgot prime prime, is at 4, -1. So this is how they take it. So they go like that and they describe it. So those are describing. And so if you were to see, like if they gave you a whole bunch of letters and you're like, what's the same translation? So let me come back to here. Zoom out. So then this is an example. Changing color. Which describe the same translation. Let's just start with Mia. Let's go like this. Let's say we had a point at, somebody tell me a point on a graph, like type in a point on a graph, like 2, 3, something like that. Tell me a point. Okay, 3, 7. This is good because if you guys all type one, then we'll have some good variety. We need variety. Can you guys type in a point on a graph? And then, so once we graph, so keep on going. I'm just going to keep on calculating stuff with it. Okay. And, okay, did we have any more? I don't want to like interrupt anybody. Okay. All right. So then the same translation is going to happen to all of these. And I want you to tell me which describes, which one has, oh wait, that's not the same translation. I'm going to do the same translation to some of these and which ones have the same translation. So let's see, I'm going to go, going to be 6 and 11. This is going to be 3 and 5. This is going to be 19 and 16, and this is going to be -1 and 5. Which ones have the same, and let me call these like, maybe this will be like A, B, C, and D. Which translations, which one, like options, A, B, C, D, have the same translation? all but B. Okay, so let's just check what that translation was. Check it. So if I went from 3 to 6, we added 3, right? From 7 to 11, you add 4. So you could say that the translation for this one would be add 3, add 4. So for this one, from 0 to that one's really easy because this would be add 3 and add 5. And let's check. From 12 to 19, we added 3. 16 to 19, added 3. From 12 to 16, we added 4. From -4 to -1, add 3. And from 1 to 5, we added 4. So you are correct indeed. B is the one that does not fit. This one is not like the others. Okay, good. And then I think we've actually covered everything that we need to do. Let me double check. Oh, you guys, I think you got this whole thing, like, rocked it here. Okay, now all of these things, this is the last thing, and then we're done with this lesson. So all of these things, we have 1 minute left. Okay, all of these things that don't actually change the size of the shape, they're called a fancy thing, and they're called rigid transformations. Rigid means it doesn't change the size. And those are what we talked about: rotations, reflections, and translations. And what else can I do on here that you need to know? I could say that this side, oh no, let's see, is that what I want to do? I could show that like this side is the same length as this side, is the same length as that side. I could say that. And then this one is the same as that one. That's another thing that you need to know. But I think all the other details, I think you've got everything, all the tools that you need to be able to pass both of those evaluations. And that is all I have for you today. So any questions? Hey, you guys are totally prepared for that evaluation. It will be next week. I might see if I can try to squeeze it in, like change the order of things, but I think it's way more work than I want to do. So anyway, okay. I mean, that it would just take a good 10 minutes, and there's no point in doing 10 minutes, just to make it a little bit easier for you guys. Okay. Same concepts. Have a good, wonderful day, and we will see you next week.